Ladies and gentlemen, I would like to welcome Devid Spergel at the stage. Devid is one of the most influential astrophysicists of nowadays, recipient of numerous prizes for what he does in research. He played a leading role in NASA mission that transformed our understanding of the early universe and launched the era of precision cosmology. Since 2021, Devid has become a president of Simons Foundation. This is a prominent foundation, leading foundation that supports basic sciences, basic research. And I'm very glad that Simons Foundation supports the summer school that currently happening at UKU and Lviv Society of Fellows as well. And numerous research projects that are done in different institutions in Lviv and in Ukraine. Today, we also honor Devid for his support of Ukraine. Under his leadership, Simons Foundation supported probably hundreds of researchers and students in Ukraine and continue doing this. As Devid himself put once, we wanted to send a message of hope, letting Ukrainians know that the world scientific community is behind them. So please welcome Devid, and thank you very much for coming to Lviv.
Thank you. It's a pleasure to be here. Pleasure to see all of you here. I mean, to me, I look out on this audience with great hope for the future of Ukraine. I mean, what we are doing at the Simons Foundation broadly is supporting basic research in math and science and trying to help it thrive worldwide. And what we're trying to do here in Ukraine is create an environment in which we can support it in a way to enable it to thrive in the future. Here, there's a great tradition here, and how do we build on this to do something significant? And I think it's exciting in that context to think about the role AI and machine learning will play in science. And this is a moment where AI has grabbed the attention of people worldwide. It is probably the most significant technical change that has happened in the last several years, almost certainly. And it's something where talk to different people, you'll find people whose opinions grow from cynicism, it's not going to do much in the end for science, to people who believe it will transform science completely. My own view is in the middle. There are areas in which it will be transformative, problems that we could not solve before that we will be able to solve. It will change the way we write papers and conduct research, as I will argue. But there's also some set of problems in which it will not be transformative. There are things it will do, but it won't do, it's a theory of something, but not everything. And we're just beginning to learn what that is. I want to begin, actually, by looking at something that I consider a bit of a failure, which is the role of high-performance computing in scientific research. And one of the things that's happened, I would say, over the last 50 years as computers became more and more powerful, we went from being able to one-dimensional equations on the computer, find the solution for a simple spherical system, to carry out complex three-dimensional simulations that advance fluids or fields in time. And that's been useful for a number of applications, but it has not changed the way we do science. I want to sort of begin by thinking about that, because I think that offers some important lessons for how we should engage with AI. Talk a little bit about what machine learning does. I think this will be review for many of you, but I think it's helpful to at least get my perspective on it. Look at some of its successful applications. And then I want to talk about, as examples, some work being done at my own institute, the Flatiron Institute, on its applications, One looking at the role of foundation models for science, and I'll show some work led by my colleague Shirley Ho, and then turn to the role of AI agents and look at some work led by my colleague Francisco Valenzuela Navarro, and Raul Jimenez, who's here and will be lecturing, is part of some of that work. So if we have questions on those things, I may just turn the questions back to Raul, since he is the real expert on here on the role of these AI agents. And then think about some of do what we call a SWOT analysis of looking at strengths, weaknesses, opportunities, and threats. And what is the SWOT analysis for AI and science? And then think about how do we want to change the way we do research to best enable us to exploit AI. And I think this is actually exciting to consider in the context of thinking about Ukrainian science, because you're at a moment of transformation. And it's a time at which one can think about how do you want to structure things in this changing environment to best take advantage of it. I mean, it's often true in technology, if you're used to doing something one way, you come in and you can leapfrog. An example is Africa, which did not have, in many places, phone lines. When cell phones came in, they didn't have to think about phone lines. They just moved to the next technology. And as one thinks about the rebirth of Ukrainian science, it's worth thinking about, are there ways in which you can jump ahead? And I don't think we know what's right yet. But I think it's important to think about as we engage with this, and then talk about how AI will potentially change science overall. So as I said, I want to begin with lessons from high-performance computing. And I think the good news is it's led us with big simulations, with big codes developed to simulate weather and climate and flow around airplanes to solve equations in 3+1 dimension in space and time in ways we haven't before. That's been useful, and it solves some engineering problems. I want to distinguish between two very important but different activities. To me, engineering is about solving problems under constraints, often constraints of resources, but you want to be able to solve a problem. Much of medicine, to me, is engineering. You want to get someone well. And at some level, you don't care why it works, as long as they end up healthy. Science should be about understanding. Now, obviously, there's a constant interplay, and a very beneficial one, between engineering and science, between solving problems and understanding. We have mostly used high-performance computing to solve problems. How do I design a better airplane? It lets us simulate complex nonlinear phenomena. It has not yet changed the way we do science. And I think that's true for a number of reasons. I think some of it is we haven't integrated computation either into the way we teach or the way we think. I'm a physicist. We still take the framework that Landau and Lipschitz gave us and still use that framework. The physics books that my father learned from in the 50s are not so different from the ones that we use today. We have not changed the way we talk about the science. We use simulation to solve a problem, not to enable understanding. We tend to do simulations with values for, say, fluid flow or explosions of stars. And explosions of stars, to me, is really problematic because we want to understand there. We actually don't care about designing stars. Where we do this to get an answer closest to reality, not to explore the different possibilities. And people have talked about simulation as the third branch of science, with theory and experiment, but it hasn't happened. And, there's been, I think that's a problem that's been true in the physical sciences and biology, in using it only as a tool to get an answer, not to enable understanding. It's also true when we look at what's happened with computer science, computation, and mathematics. It is applied math has sort of had a complex relationship with computational science. Computer science departments in most places, and I tend to focus primarily on discrete mathematics and really aren't interested in using computers to solve partial differential equations, which is most of what we do as physicists or engineers. And there's just not been as fruitful a relationship as there can be. And I think this is a very important lesson for AI and machine learning. Right now, certainly in the US, but I think worldwide, there's an enormous amount of resources going into AI and machine learning, driven by companies like Google and Meta and so on. They are interested in their bottom line. They want to solve problems. That's fine. I think there's, I appreciate when I can use Google Maps to get around Lviv. There are useful things about these things, and that's useful engineering. It doesn't enable understanding. And much of the attitude in the AI community is focused, so engineering focused, I think we will miss opportunities to use it as a way to enhance understanding. And that means really getting at what goes on in models. And I think this really, of course, depends what you're coming from. I know this is a meeting on AI in agriculture, and if you're interested in increasing productivity, which is really important, that's great, and that's a great outcome, but you won't understand plant science just by running an AI to improve it. You need to dig deeper into it, and that's a different way of thinking about the tools. And we're going to need to adopt that, not for everyone, but those of us who are scientists engaging with AI need to think about, how do I use this to increase understanding? And sometimes that will take the form of using the tool, and sometimes it will take the form of really digging in and understanding it. And I think the same is true, talked about computer science and mathematics, in terms of understanding the mathematics of machine learning. We treat machine learning almost like it's a miracle that it works. But fundamentally, this is about the mathematics of functions in high-dimensional spaces. Fundamentally is about how we do probabilities in high-dimensional spaces for next word prediction or understanding that. And we need to develop a more sophisticated understanding of mathematics in high-dimensional spaces and probabilities to be able to exploit this. And this is a conversation I've been having with some of my colleagues thinking about teaching machine learning. What do you want to teach? Do you want to teach methodologies for solving problems? That's important. But I think also, you need to be able to understand what's going on. Both my younger children, particularly my youngest, is involved in using machine learning. I was horrified that people can study machine learning without learning linear algebra. It's, you need to have the basic tools. One of the things I required of my 3 children, and 2 of them are history majors, was you've got to learn linear algebra, before you go on in life. This is sort of a minimum literacy requirement for life. So let me just do a little, at least my perspective on why I think machine learning works so remarkably well. And I think of starting with pictures of cats and dogs. If I take a picture with my cell phone, 10 million pixels on my camera, 3 colors, it's a 30 million dimensional space. Every single picture of a cat and a dog is a point in a 30 million dimensional space. Now, if I was going to tell you about fitting a surface in a 30 million dimensional space, from what I learned in numerics, I'd tell you it would need many, many hundreds of millions of points, right, to be able to sample and interpolate. Yet, if you give a network 10,000 labeled pictures of cats and dogs, that's actually enough to train the network to distinguish with a pretty high accuracy between cats and dogs. Why does that work? That's because the group that is cats, and even the group that are dogs, ranging from dachshunds to Great Danes, actually occupy a fairly low dimensional space in that 30 million dimensional space. There are a lot of diffeomorphic symmetries. I can distort the image a little bit. Doesn't change that much. I can certainly do translations and rotations, still the same thing. But there are many local smooth symmetries that don't change the image much. And that means it's represented by a fairly low dimensional space. And things like conformal neural nets can do a pretty good job of representing it. What has been incredibly exciting over the last several years is how large language models have transformed our understanding of language and language transformation by doing next word prediction, right? That's really all they're doing is given previous output, words in the sentence, you train on a big set of data, you predict the next word. And what we have learned is that language occupies a fairly low dimensional space. That when you have a sequence of, say the 100,000 words, and typically in a language, in a 1,000-word sentence, right, you've got that's an enormous dimensional space that you think about there. Yet, these large language models are large, but nevertheless, the number of variables is small compared to the points in the space. And you can, with enough data, train on it. And these transformer architectures have turned out to be a very useful architecture to do these sorts of next word predictions. So, machine learning works really well because of these symmetries. Now, the symmetries are helpful. There's also 2 other elements which we will come back to as we talk that are essential for its success. One is compute. You need a lot of compute. And the other, and there's been talk about that, but I think what's actually more important is you need an enormous amount of data. And what's been important with the development of these large language models is there's a lot of data available on the internet for free, and most of that data is pretty good. There's a lot of nonsense on the internet, but you can learn a lot about language and its structure and information there. As we go to think about AI for science, one of the challenges is we actually have, and this is what we'll get to at the end of the talk, we have a limited amount of data available. Data is expensive to obtain in many areas. We haven't made it available in forms that are useful for AI to use. And we're going to have to learn, and this will get to our discussion of pre-training. What do we do when we have a limited amount of data applicable for a problem? And that's, I think, going to be some of the drivers as we think about machine learning for science. Let me just mention some successful applications. I'm an astronomer. You look at stars of different types as a function of their brightness and color. Don't worry about the axes, it's just brightness and color. Stars represent a very low dimensional space. You tell me a star's mass, you've told me most of what I need to know. You've told me its chemical composition or age. It's a small correction, right? But it's a low dimensional space, so I can go observe things and say, hey, that doesn't look like a star. That's interesting. And I can find interesting objects. So it's very good at outliers. It's also very good at representing complex functions. And the most dramatic success of machine learning, one that enabled Nobel Prizes, is protein folding, where this was a problem that simply could not be easily solved, and it has produced very interesting results. Results that I'd note don't change our understanding of protein folding per se. It really is just a tool, but an incredibly powerful tool that I think will lie behind advances in drug design and many applications in the coming years. Some progress in things like suggesting new equations. To me, and I think one of the very useful, just not understanding, but just enabling of science things, it is much easier to write code. I now do all of my coding using things like Coursera and ChatGPT. And I think for students coming up, that's how you're going to do it. There's a separate and interesting discussion for the people teaching computer science, is how do you teach people to code in a world in which you can do this? Because for experienced programmers, it's an incredibly powerful tool. But it's not it doesn't write great code on its own. You need to have a sense of how to guide it and how to structure things. So how do you do this? How do you teach people how to do this when they're going to rely on this tool? I think about it in terms of ability to do arithmetic. So my grandfather, who was not at all an educated man, but was a smart guy, used to be able to add and multiply 4-digit numbers in his head. Right? He would just do that. And he was like, lots of people used to be able to do that because they didn't have calculators, so they taught themselves how to do this. I'm young enough that I had a calculator, so I don't do things like that. I could at least add the first digit in my head, which, amazing to me, I've discovered people in our accounting and finance department can't do. They give me reports. I'm now, my day job is still mostly president of an organization, and people give me reports, and I look at the numbers and I say, 3 and 5 and 7, that adds up to 15. You're telling me that's going to cost $2 million, not $15 million. There's a mistake here. It's like, how can you tell? I said, one of your numbers are wrong. And it's like, because I can do addition. It's a secret power I have. At least sometimes even 2-digit numbers. Okay, but let's get back to coding. Stop bragging about my ability to add 7 and 8. The next generation of programmers are going to start out using large language models. So how are we going to teach them? So a question I don't know the answer to. We have to really, but I think it's an example of how we have to rethink things.
May I ask?
Yes.
How many programmers these days know how to code in assembler, how to machine code, that you can actually give them a Turing machine and they can actually program it?
Kendrick Smith.
Okay.
So, okay.
That's a great answer.
So
that's 1 out of 100 people that we know.
Right. So Kendrick, who Raul and I both know, is someone who optimized the computer code to look at data, radio astronomy data, and to analyze data in a way that no one could before, because he knew how to make the code run incredibly fast, because he could get down to the details. So, you know, higher level, how do you write in ways where you have higher level languages? So we'll go off on a little computer science tangent. I learned to write in fairly low, not in assembler, but we learned in languages like Fortran and C. Now, then people move on to languages like Python that were higher level languages, and in fact were in many ways more enabling. And while, but I think one still needed an understanding of algorithms. So you still need to teach sort of the core ideas without forcing people to learn assembly. So I think we have to achieve this balance, and it's not an insoluble problem. We've had this before, but as I think we think about how scientists will use AI and how programmers, we do need to think about this. And you know, one of the really powerful things that it does certainly very well is exploring literature, and we'll touch on that as we talk about some applications. So let me, and I'll move this over, talk about one example of things that we've been doing at our institute. So the Simons Foundation puts about 80% of its resources into supporting grants for programs worldwide, like this conference. We put about 20% into our own internal institute, the Flatiron Institute, where we support about 500 researchers. And one group we've had has been led by Shirley Ho. It's an effort we call the polymathic program, trying to apply foundation models, the same kind of models that are used for language, for science. And, you know, language, our understanding of science is based on more than just language or videos. It's based on scientific data and mathematical models. And the large language models are not really designed for that. So if you look at something like ChatGPT and apply it to weather prediction, or you apply it to, you have an equation, a dynamical system, you want to predict the next step, it's not good at it. It tends to not be good at that kind of extrapolation. It's actually also probably why ChatGPT has not been used successfully for financial prediction. You can take all the financial data you have and try to predict what the market will do tomorrow. And as far as we know, no one is making tons of money that way. And I've actually know, because of the nature of the world, I know lots of people trying. And that has not worked. Thank you so much. And so one challenge is these models aren't right for it. Another challenge is the data. So the big success has been, thank you, protein folding. Protein folding relied on the protein data bank. It took $5 billion of experimental work to build up the protein data bank. And that was done in a very careful way that enabled machine learning. And that's, I mean, this is a great success. I don't want to take anything away from it. But it means to have other successes like this, we will need to find other ways to, to generate a lot of data, and data is expensive. And then, this is even true for language generation. I mean, if you want to teach a large language model how to use a word, the number I've been told, and I'm not expert on this, but it takes roughly 1,000 uses of the word. I can tell you, as someone who once raised toddlers, all you need to do is hit a nail once and have your hammer hit your finger and shout out, "fuck," loudly. Your toddler will immediately learn that word and will repeat it to the grandparents the first time they see it. So, we are much better at one-shot learning because we understand what's important or what's not in context in a way in which a neural net doesn't have that kind of emphasis piece. So, it's a challenge. And, this is just another kind of a visualization of this. These large language models have been designed to take text and image and audio and video and predict what's next. And they do an incredible job. I don't want, but this isn't the same thing we're doing in physics or biology or chemistry. We're going to need to have a different way of approaching these models. So, different approaches that have been taken by our polymathic team. We're treating quantitative data differently. We're not just treating as a channel with values from 0 to 225. We're training the models to take on heterogeneous data. There's actually a lot of useful information in papers, if you sort of focus on refereed scientific papers, even in Facebook comments and subreddits and discussions, and trying to sort of imbibe the model with training on that as ways to approach it. And trying, at this point, trying to take data from a lot of different areas, combine them together. We have for this program, about 100 terabytes of data that are with many different modalities to train a model to do this. And one of the things that's been a focus is on fluid dynamics and training the network to do fluid simulations and to do next prediction on fluid evolution. And one of the key things there is that we can train the models knowing some of the physics, knowing that we want to be able to take observations of temperature, pressure, and speed. Those are the fundamental things that we want to do at. And making a lot of use of pre-training. So one of the challenges here for, say, and we'll dive into this a bit more in these fluid models, is running a fluid dynamics simulation is pretty expensive. And running a simulation as we do of like merging neutron stars or the biology of cells, that will take days of supercomputer time. So you have hundreds of examples. So you have to find ways of pre-training on data that can give you the model an idea of what to do. Now, what do we mean by pre-training? If I start a machine learning model, the standard thing to do is the model has a bunch of weights that you have to put into its evolution. You put in random numbers for the weights and start and run the model. That's sort of starting it without any knowledge. I'll show us in a slide or two. You actually do much better if you take the model and give it a lot of cat videos. And your first response should be, cat videos? What do cat videos have to do with simulations of neutron stars? Actually, a lot. Cats conserve mass. They conserve momentum. They conserve angular momentum. Cats do not suddenly bifurcate into multiple smaller cats. Ideally, unless you're doing something terrible to the cat, pieces of the cat don't go flying off in random directions. So all of those cat videos, and it turns out, for reasons I don't fully understand about human nature, YouTube is filled with large numbers of videos of people's cats. I would not record, I don't have a cat, If I did, I don't think I'd record large numbers of videos of it, nor would I post it to the internet. And I certainly wouldn't watch videos of other people's cats. But there's clearly a market out there, and that turns out to be useful for pre-training. And for training on fluids, it's turned out that even using things that are very different. So if we're interested in training on incompressible fluids, using training data from simulations that are highly diffusive, subsonic, nearly supersonic, so very different regimes, but still the same fundamental equation, turns out to give you a situation where you're closer. And again, knowing what we want to keep track of, that the fundamental things are velocities and densities and pressure. Here's some networks trained on simulating the evolution of supersonic gas. And you can see the predictions in the ground truth are pretty good. That with the proper pre-training and relatively few simulations, we can do pretty well. And let's see if this works. Oops. Somehow I was supposed to get the simulations running, but all right. And this is some quantitative things. As we look at starting from scratch in terms of how many samples it takes. So this is looking at how well you reproduce the results. So that's the goodness of fit on the y-axis. Number of simulations you need to train the networks. And the different colors is how much pre-training you do. Going from, if you start with, these are, just random inputs, you can see that this is effectively our cat video level pre-training. It's a factor 2 better than you do otherwise. And this improves more as you train on simulations that are near to you. So you can learn a lot from that. And we've been using a bench point of PDE simulations. And what the team has done is they've now assembled a whole set of 3D simulations from a wide range of fields, a total of 55 billion tokens with 30 million frames. And the idea is to have something like ImageNet. ImageNet is a set of images that we use to train networks that played a very important role in the field. To have a series of available simulations that people can use for physical training. And all these are available freely, and the goal is to try to make this accessible for everyone who might be interested in training physical models on these equations. And in a sense, this is, if part of the problem for applying models for science is you don't have enough data, well, let's take the data we have and make it as available and useful as much as possible. And here's an example of some models trained on it. So let me turn to 2 applications. One is looking at weather on the sun. There's a lot of work done on Earth weather, but solar weather is actually quite important because solar flares rain down on the Earth, affect our electric grid. The most dramatic solar flare was one that set off what was called the Carrington event in the 1840s. This was a very large solar flare that knocked out the telegraph systems across North America and parts of Europe. In the 1840s, we didn't rely on electricity that much. If a Carrington event happened today, it would knock out the power grid for roughly half a year for about half the planet. That's a pretty devastating event from the sun. And we know from the Carrington event, which is about 150 years ago, and observations of stars like the sun, that these happen once every 200 years or so. They're not uncommon events. We'd like to be able to predict them. So that's one motivation for this. And yes?
This is a good example of where high-performance computing didn't bring anything to the field, because people have been modeling the sun with high-performance computing for decades, right? And it still remains an open problem, as you say.
There's a bunch of problems with solar physics. I hope there's no solar physicists who will offend. So one of the problems is a cultural one, that they isolated themselves from the rest of physics. Another one's a methodological one in that they didn't make their codes available to each other. So everyone had their own private code that got their own grants, and they wouldn't share data. They really didn't take on the big problems of understanding fundamentals. One with enormous application is genomics. You know, we have a large amount of curated genomic data. What we really need to get more of, and this is something that, you know, because as a foundation, we've been very interested in supporting research in autism. We've been very interested in getting a lot of genomic data, a lot of phenotypical data, a lot of developmental data. Try to get this in the form that we could use this. And it's already clear that the kind of tools that people have used with GWAS, which is sort of linear modeling of genomic data, is limited. And we need to make use of nonlinear things, and machine learning is good at this, for getting understanding of polygenics. So here's some examples of solar flares. And do I have a movie here? Yeah, so here's a movie of the evolution of magnetic fields on a sunspot. And just like, in the sense, language models predict the next word, the idea here is to, based on what the sun looked like yesterday, predict what it looks like tomorrow. And these are sort of initial results that shows that this kind of approach can be quite promising. Another piece is trying to use software for protein design with AI agents to explore the space. And this is sort of the next piece of the story I want to talk about, which is using AI agents as ways to explore possibilities. And now I'm going to, actually before I do that, let me just say a few things about thinking about how to do science with deep learning. I think one of the key things is get as much training data as possible. About 20 years ago, when Barack Obama got elected as president, his campaign manager had a simple slogan about politics: "It's the economy, stupid." And that became a famous quote. So when I think about AI and machine learning, I think it's the data, stupid, right? The model is never better than its training data. You give model lousy training data, it's going to have problems. So the challenge is going to be, how do we get good data? And that's just the start. We're going to have good data that's accessible and usable. We're going to have to design a neural network architecture that's optimized for the data. And the transformers of large language models were meant for large language models. They're a useful start, but they're not going to be the definitive answer. We're going to have to deal with data processing issues. We're going to want to pre-train, run on GPUs, and then, you know, once you've trained the network for your problem, you kind of throw the network away. And then you need to learn, what did the network tell you? And how do you probe the network to get an underlying, to get more than just a result, but to get what our real goal is, which is understanding. So now let me turn to AI agents. And this is work led by Francisco Velasquez Navarro. We call him Paco, so I will abbreviate this as Paco for the rest of the talk.
Even for us native speakers, his name is too long, you know. His name is far too long, so we call him Paco, that's it, yes.
So, and these AI models, AI agents, let us basically run different kinds of models, let us access and do different things at once. We applied this, or Paco applied this in cosmology. So here we had a set of training data where he had done previous work, where he ran a large number of computer simulations exploring different cosmologies. And the philosophy in these simulations were different from, let's try to generate a simulation that looks as most like the universe as possible, but rather to run it with a range of different parameters to understand the relationship between the parameters and the underlying physics, the outcome of the model, as you change, in this case, how explosions work from supernovae. He and his colleagues had written a lot of documentation, so they had access to the documentation. Over the last 5 years, since they've been generating this, roughly 100 papers were written by the people who are part of the team, but many people in the scientific community made use of this. So he had 100 papers to train on. And more generally, the broader archive of scientific papers to train on. And, you know, then they created code that were tailored to use this. So they started by using this to write code that could query the data on a sort of case-by-case basis. So they understood how to do this case by case, and then set up to do a multi-agent approach, where they would, like ChatGPT, search the literature, but had designed it to search a limited set of literature so they knew that they were dealing with things whose quality they understood. Based on that, they would generate hypotheses. What are some ideas that might explain the data based on what is in previous papers? That's good. I'd note that that doesn't let you get outside of the set of ideas you've had so far, but that's a start. And
the key of this hypothesis is that then you generate an adversarial network, right? Do you have an adversarial collaboration? Exactly, that's the whole key, right? Then you can just collaborate and criticize each other.
So the code can do it. I think what's important is you can also draw ideas from outside the area that you're familiar with. So one of the games I played with Paco on this was, I said, take ideas from polymer chemistry, where you have bubbles and voids, and apply that to galaxy simulations, where you have galaxies and voids, and make use of mathematical concepts that you haven't seen before in this part of the literature, and apply it. And one of the most interesting results that I thought that this team got from this was using ideas from tensor networks, from quantum materials that have not been applied in cosmology, and a literature that the network was trained on, but were not familiar to people in the field, to propose ideas. And the way this is structured is not only does this one agent generate hypothesis, it writes code to look at the data, test the hypothesis, does the data analysis, generates the needed code, as I've mentioned already, cross-domain reasoning, it will write a draft of the paper, and it will critique the paper. And different agents play all of these roles. So you can basically give it a data set, and it will generate a series of papers very quickly. And the papers, they're not terrible. They're not transformative yet, but they're a very useful tool. And, you know, the threshold problem I think of is general relativity. Einstein coming up with general relativity, to me, was one of the great ideas of science of the past 100 and 120 years. Einstein, I don't see in its current state how these kinds of models come up with general relativity. What I do see is if Einstein had it, he would have been able to do queries about differential geometry, got pointed in the right direction more quickly, would have explored some of the failed ideas he tried. Einstein tried a bunch of things. In like 1912, he's living in Prague, he hates it. He tries going through the divorce, lots of bad ideas, they don't work. He could have tested those ideas faster. So it's not that this replaces scientists in any way. This lets us do, I think, in many areas of science, things more effectively. And I think it's a tool for solving problems. And I think that's, you know, it will let you go through this process of given input, given data, and data is really important. Here we have the simulations. Data is also the paper, the literature. Generate potential ideas. It will generate a research plan. It will generate code, and will let you explore these models. And that lets you explore the space of possibilities faster. And there's a set of things where that will be useful for. We already talked about the importance of you need to not only generate ideas, but critique the ideas. And this is something that I think we're going to have to figure out how to do as a scientific community more effectively. Because to me, one of the worrying things about AI for science is it's going to let you write a lot of mediocre papers really quickly, and will generate a lot of poor quality stuff. There's already too much poor quality work in the scientific literature, and this will only make it worse. And we're going to need ways of thinking about how do we filter this. Let me talk through most of this already. One implementation, and this is something Raul's been part of, is using Denario to sort of go through paper generation. And what's been fun to see, and there's a paper in preparation that will be out soon, I hope, that uses the same tool to generate papers not only in astrophysics, but in public health, in chemistry. Failed to do it in math, which tells us something about math. It has some protein folding cases. There's just a pretty wide range of applications. The most novel ideas, I went through it, seem to actually be in its public health work on IVF success. And people looking at IVF in vitro fertilization have been only comparing clinics from clinic A to clinic B. They had not looked at the trend that effectiveness of IVF was fluctuating over time, certainly due to things like COVID, but even seasonal variations. And that was in the data, but the people looking at it hadn't thought of looking at it that way. And once you've seen that, the paper they wrote on that is not the best paper that could write. But what it says is you're a researcher doing that kind of epidemiology. Hey, this is something that you've missed, because people in other fields are used to looking at time sequences like this, but you haven't because you're coming from a certain perspective. Look at this. It's not the final result, it's the start. And this is sort of the first application of this in this field. And that's an interesting start. Again, it shows you the importance of data. You need to have this large data set, and you need to have a data set in a sense that people haven't looked at in some way to see something new and insightful. So now let me turn to looking ahead and thinking, what are the kinds of problems that AI will likely solve? You know, there was a sort of what is the next Nobel Prize, where the work in the prize wouldn't have happened if the scientists involved hadn't used AI, right? And it's not that it will be used for every problem in science. Advances in instrumentation, novel ideas for mathematics. There's lots of things that will happen that won't use this path, but it's going to be a really important path. And because we have a new tool, it's something that I think will be really important in the next 10 to 20 years. When I was a postdoc, my mentor had a sign over his door, a guy named John McCall. It's a quote from Hans Bethe, one of the great physicists of the mid-20th century: only work on problems where you have an unfair advantage. And I asked John what that meant. And he said, well, you're not going to be smarter unless you're than everyone before. So you have to come at it with something new. And whether it's a new experimental technique or a new theoretical idea, you have to come at it with a new way of doing it. My point here is, in these various areas, AI and machine learning is a new tool. It's a new way of doing things. And it has a chance, I think a good chance, of leading to something that might be transformative. So drug design we've already mentioned with protein folding. You know, basically you can now say, with this protein I get something shaped like this. I will show you my understanding of biochemistry. If you want to have a drug that addresses a disease, if the thing you want to kill looks like this, you need to design a drug that looks like that, that binds to it properly. And you want to have a high binding efficiency and not have it attack other parts of your body. So that's a big space to explore, and that's what it'll be good at that. I think similarly, it's going to really help us develop novel materials for a wide range of uses. There's things like thermoelectric materials where our efficiencies are really low. We can really make a lot of progress on energy if we can design new materials. There's a lot we can do to improve human life if we can just explore the space of possible materials. Some of this we will do off of experimental data. To me, what's really exciting is the possibility of doing this from first principles, starting with the fundamental equations of quantum mechanics and solving the Schrodinger equation. And the problem there has been, you know, they taught me as an undergraduate what happens with hydrogen and one electron. If you start thinking about what happens with tens of electrons in an atom, or hundreds of electrons in a molecule or a complex material, that's a very high dimensional space and very hard to characterize, or has been hard to characterize. Machine learning turns out to be neural nets are really good at characterizing things in high dimensional spaces, and especially when symmetries produce you to a lower dimensional subspace, even if the symmetry is partial and not complex. That's complex materials. And I know from my colleagues working in this area, neural nets seem very promising. So I think we have a good chance there. Another area is catalysis. The Haber-Bosch process by which we make fertilizer. It's the same process we've been using for over 100 years. It uses up over 1% of the world's energy. It's responsible, I think something like 90% of all food eaten by humans relies on fertilizer that uses the Haber-Bosch process, right? And that's like, you know, Haber and Bosch were good chemists in 1915. We haven't done better, and there's probably a better way to do it. And you know, I think it will help with exploring those spaces, and that's just one example of, you know, catalytic reactions are so fundamental for so much of the chemistry we do. High temperature superconductors. If we had high temperature superconductors that worked at room pressure, you know, it would have enormous impact on our ability to generate energy. We could generate, you know, you can fill the Sahara with solar panels and power Europe, right? There's, alternatively, if we can do controlled fusion, that's another one. Now, controlled fusion is a good example of one where one of the challenges in doing control of plasma and training a neural net to control the magnetic field to keep the plasma under control is the experimental data you need to do this is very expensive. It takes about a week of running a tokamak, one of these like experiments in France or the big stellarator in Germany, to collect enough data to get a data point. So you might have a few hundred data points if you're lucky. And the networks are not optimized for this, you know, this limited data regime. Turbulence is a problem that's been around for over 100 years. We understand the fundamental equations. We don't understand the properties of their solutions. Yet if you look at a turbulent flow, you look at a pot of boiling water, you look at a river, you see both the regularities, and by eye you have a sense there seems to be some regularities here. You know, I think machine learning can be quite useful there. The thing that might affect human life the most is our ability to understand polygenic disease. Right? Much of what we understand deeply in medicine is sort of the simple stories of things like, you know, these diseases where you have a single mutation, sickle cell anemia. There's a single mutation. It was evolutionary adopted for if you have an environment in which you have one of them, you have two, it kills you. And it's a single mutation that causes the inability to produce a single protein, and it's impressive. We understand that piece of biomedicine well. Most stuff in life is polygenic, and it's not just multiple genes, it's the effects of environment. And some of this is just the effect of evolution. We have been selected to be robust against small mutations. Most mutations are neutral, so most diseases, whether it's cancer or schizophrenia, are not single gene. They're polygenic and depend on environment. And characterizing these nonlinear things, I think neural nets may give us the tool to do this and to really make breakthrough understandings there. More broadly, I think that's telling us about evolution and complex processes. It's certainly already telling us about things like the ability to do weather predictions, where we have lots of data and don't really understand the scale physics. So how do we best take advantage of this? How do we restructure science to do this? I think there are two key pieces. One is getting scientists ready. The other is getting the data ready. Getting the scientists ready, I think of it as having two pieces. We want to take already active scientists, people who have been chemists in their labs for 20 years, and at least offer them a summer program so that they can understand when AI would be useful for them. And even if they're not users, they become suppliers, that they do their experiments in ways that can be utilized by their colleagues doing that. And another is and again, I think we really want to take this, to me, this is trying to take some of the lessons from computation. We want to incorporate AI and machine learning into the curriculum. Think about ways in which, and this is true more broadly than just the sciences. You know, if you're training someone as a historian, you're no longer going to ask a 14-year-old to write an essay on the causes of the First World War, right? Because you can ask a ChatGPT to do that. You're going to ask them to use ChatGPT to come up with multiple explanations. You want to teach them to be a critique of it, to understand how to write an essay comparing the different ChatGPT versions, at least, right? And, you know, and understand how to use these tools. So I think it will change a lot about how we do research and training, and we need to think about it. As I tried to stress, AI relies on the data. Without data, it's nothing. And, you know, I think we need to be able to start to provide large, uniform, open data sets, be good about data curation, very importantly, data validation. And I think it'll also be quite enabling, is if we make data open and accessible, it's much easier to find fake data. And it's going to improve reproducibility, and it's going to help identify fraud. So I think the process of making data AI ready will improve science. You know, what are some of the dangers of AI? And I may be too much of an optimist, but I am actually not worried so much about the killer robots. I'm more worried about low-quality papers. Because I'm confident there'll be low-quality papers. And another piece that I'm confident will be is fake experimental results. Because it's going to be very easy to generate that. And I think one of the claims, and I've not seen this well documented, but many people have said to me that the quality of large language models is in some ways decaying because the data they're training on is getting worse. And there have been
just a couple of comments on this. So that happens with the early models of Google Translator. Because what happened is that they got this translation to work 10 years ago, I'm talking before LLMs, on some curated data, right, from experts, right? But then some genius in Google said, oh, let's just train on the internet, right? So Google was training on itself, right? And then translation quality degenerated completely, right? Because it was a completely never-ending process. The other comment on the first point is that we have seen the increase of production of mediocre quality papers much before, right? That's when LaTeX came to the ground. And then you could just cut and copy and cut, you know, like a cut and copy. So basically you could just produce papers. When you had to write the paper by hand, right, you were very careful to decide what you wanted to write because it was a lot of physical effort to actually produce the text, type it on a typesetter, produce the plot, right? With we have seen that, right? I mean, and we both have been complaining about the huge amount of wasted postings on archive because people have this ability to actually just cut and paste, right?
So to add to your list of desperations there, which I can read, I'm a pure mathematician, and my concern is inability to judge what is true. Because the moment, you know, the moment I say, or any mathematician says, that you cannot efficiently referee a paper written by AI, one would say you cannot efficiently referee a paper written by whomever because, you know, like average paper in math is 60 pages long, no one has time to read it. All true, but we have, you know, as we are educated in mathematics, we are in particular educated on the ways people bullshit. You know, I can judge an oral exam of a student in 20 minutes very efficiently. You would say, how in the world they don't prove a theorem in 20 minutes? I know all the ways in which they can be wrong. I can push all the buttons they have very fast. Similarly, with the scientists, they give a presentation or they have a research paper in your subject. No, you are not reading 60 pages, but you kind of know the weak points because they were your weak points one day because you've been over this over and over. And the problem is that the way AI or any sort of, similar machinery makes mistakes is not the way we make mistakes. And the way they bullshit is not the way we bullshit. And there have been so many ways, so many attempts to write papers which sound perfectly conceivable because you just don't bullshit the same way in a sense. So I would say, the bigger problem in this, and maybe physicists care less because 99% true is kind of true, but the mathematicians it's not. The biggest problem is that we will not know anymore what is true. And we will not be able to teach our students anymore what are the logic rules, that there is absolute truth, that sometimes it implies B and sometimes it doesn't. And if most of the times it does, it's still not, there are rules of logic which you have to be able to teach and to learn in order to do all of this. And my worry, for instance, on top of mediocrity and the amount of data and all of this, is that we will simply lose the concept of the absolute truth. And I claim it's an important concept, even if you don't do pure mathematics. It's kind of important to know what's true.
No, I would agree, and my generalization to science would be loss of understanding. That, I think what's important to me in science is that you understand something about the universe. That's what we're trying to achieve. And to give a practical example from medicine is aspirin. For a long time, people would say, we don't understand why aspirin works. It does, and that's all that matters. It took a very long time before people actually understood the mechanism. And to me, AI is going to make it easy to have a result and not understand it. I think the example you're giving is another aspect of this. You'll have a result that looks correct, but isn't fundamentally correct.
But I'm worried about the generation of people who don't even know.
Yeah, I think this is how will we train people, whether it's as computer scientists, or mathematicians, in the world of AI? Because it is a tool that has power, but it's also a tool that I feel sometimes like we're giving Ferraris to someone who's never driven before, and they're likely, people will use these in ways in which they will produce intellectual crashes. And how we should think about what comes out of these networks is, in all these fields, I think is something we haven't figured out yet. And in a sense, the flip side of it producing poor outcomes is it will also produce powerful outcomes, so that we need to understand it. And there's this issue of generational divide and resource divide. Is we'll have people who are kind of AI natives and know how to use it effectively. Some of that will divide on age. Some of it will be, sometimes, we old folk can retrain ourselves a bit, but most don't. There's also a resource divide. At the moment, and this may change, but to train the current large sets of large language models, you need access to enormous numbers of GPUs. And the estimate I've heard recently was will be, in the next 10 years, $2.6 trillion invested in data centers. Right. And the energy use. There's the energy problem. A piece of that, I think the answer is, They're building lots of cheap nuclear power plants soon next to the data centers. So I think we'll have some control of that with the data centers. We have to think that through a lot. But there's an access question of, right now, to have access to the compute to do these models, you sort of have to be working for, one of 5 companies in the world, right? And I think this is, as one thinks about, what is Ukraine's role in this world, right? Ukraine will have access to some of those resources, but it's not, we're worried in the US about how our universities will keep up when they will not have access to the compute available. Something we're doing in New York State is we formed a consortium that involves about 2/3 state money, about 1/6 institutional money, about 1/6 foundation money, and discounted prices. So we'll have $1 billion supercomputer available for New York State scientists. I can imagine Norway or Switzerland or something doing that, but there aren't that many places that will have access to that level of resources. And will that mean that people will be left behind, or will there be clever ways of doing this? And I don't know the answers, and I think these are problems we have to deal with. And I will end by saying, will AI change science? I think yes, it's going to change it. It's going to change it some ways for the many, many ways for the better, in some ways for the worse. If I was sent back in time and, I lived through the development of the internet, and is the internet a good thing? Probably. There's ways in which it's made society coarser and worse. There are ways in which it's made it better. I'm not even sure, having lived through the last, 30 years or so when the internet took off, that I wouldn't be sent back in time. I would know what the right policies are to improve things. One of my favorites is no cell phones for anyone under 21. Maybe 25. But, just the flip phones. But there's, it's... Good luck trying to implement that policy. Wait. Talking from experience. This is a father of 2 teenage twins. Who lost his hair. So, I'm going to end just by opening things up to questions and people's thoughts. And I've tried to raise these challenges. I think it's a time of opportunity, but we need to figure out how best to take advantage of this. So let me just open this up, and then I'm just going to pass around the microphone, and we'll just kind of.
Thank you, David. And just about teaching, I think the demand for paper will rise. So many teachers consider turning back to paper exams, for example.
I think paper exams, I think oral exams become more important. I think we need to change the way we evaluate faculty. We simply do not look at numbers of papers ever again, right? We ask people, what are your 3 most important papers? And that's all that matters, because it's easy to generate large numbers of things. Like it's your 3 most important papers, the students you've trained, the classes you teach.
Yeah. Okay, I saw already 3 and 4 hands, so I'll start with. Okay.
David, I travel thousands of miles to listen to your review, and it's wonderful, especially from your point of view. Thank you. I heard many thoughts of yours about expertise, quality of good fundamental science. And my question to you, when young people have access to tools immediately, and they feel they know everything, where is the place for that expertise which comes with years of doing good research, creating this fundamental knowledge, which is a foundation for AI and machine learning? Because people who do this real fundamental research provide this quality data, provide this data for the future tool to be used to maybe learn more. So it's like generational gap now. So scientists who spend their lives producing good knowledge, understanding, and data, facing young generation which is aggressive, eager to do something to be successful, and they might not overlook all of that history of science being a way of learning and understanding the universe. How would you approach that problem from your wonderful experience? Thank you.
So thanks. This is a question I've been struggling with because I continue to train students, many of whom are using machine learning. Many of whom are still using machine learning as a tool. And I've been trying to push them, and this is true of any new tool, okay? It's like, it's not that you want to apply the tool for sake of applying the tool. What matters is the questions you apply it to. And you have to teach them taste, right? And I think this is something in science and math that's really important, is taste for an interesting problem that has an important impact. And that you want to apply machine learning because there's an important problem that you couldn't solve before that you now have the data and tools to do. You have to start with the problem, not start with the method. And people get excited by the methods. It's a failure mode I have seen is people applying known methods to existing data to get uninteresting results because they're not asking interesting. And there's just a, I would say in my field of astrophysics, 90% of the machine learning papers fall into that category. And they're not interesting computer science. Right? There's interesting, if I'm a good computer scientist, I want to take, these methods and develop new methods, or I want to understand the methods. That's important work. Or if I'm a mathematician interested in machine learning, I want to understand the mathematics of why this might work and what conditions. But like just taking a tool and using it to show you can use it, it's not a bad exercise to do in class to develop it, but that's not going to lead, and maybe you do this to train yourself, but that's not what leads to novel insight.
Thank you.
Thank you very much. It's really very interesting, and will all change, artificial intelligence change the science? Yes. Yes, but I think that different science in different scale. For example, if we talk about the chemistry, a lot of things in chemistry will be key point as an experiment. And in such science like chemistry, especially in experimental synthesis, artificial intelligence will be very useful, but not a key. So when we want to tell yes, maybe sometimes yes, sometimes no, sometimes useful, sometimes useful as consultant, but not a key performance.
No, I would agree. I think it's going to really depend on the nature of the problem. There'll be a set of problems where there are things you couldn't do before that you can now do. I think in fields like chemistry, biology, many areas, it will make you collect data in a different way. So the data is AI ready. That in of itself may be useful because it will allow intercomparison ways you haven't done it before. And there are certain ways of exploring certain spaces it'll do really well. It won't solve every problem, but there's some interesting set of problems it will solve. And I think the problems it won't solve, maybe someone has a great idea on, but I think we'll see over the next, say, decade or so, the areas in which AI can be transformative are the ones where it will be transformative, so the progress we'll see in science will be more AI-driven initially. I mean, it's a lot like, I mean, the technology that I think has been most transformative that I've seen in science outside of this is CRISPR in the last few years. It lets you do biology experiments in ways you couldn't before. And I think we're in the midst of seeing kind of a CRISPR-driven revolution in that there are certain problems where it just changes everything, and we'll see progress in those areas, and we'll see less progress in the other areas just because we don't have new tools. We're just not, you know, we're just not smarter or more enabled. So I think what we'll see in chemistry, biology, physics is a bunch of important results in the next 10 to 20 years that are AI enabled. And depending on whether AI saturates in its capabilities, we may see sort of a bump, would be my guess, where we learn how to solve those problems, we solve those problems that we could solve, and then move on to other things with other methodologies.
Thank you. We already had a question from biologists, from chemists. Now, let's go here. What field? Computer science?
Computer science, second year, bachelor studies. Thank you, David, for such a fine speech. You gave me a very broad perspective on AI. And I want to ask you a question about large language models especially. Like, you mentioned a problem of very bad data. And an idea struck my mind that we want to teach AI to think as humans do, but like we teach it on data sets, like on papers, on text, on books, but these are just a result of human brain activity. But what if we use a technology which was created by Meta, I don't remember, which can like read human thoughts and like give people some hard problems and like scan their thoughts, and then some intelligent people, some scientists, and then AI will learn how to think like intelligent people do. Like how to think, not just to how to imagine it and produce the next most possible world.
Yeah, I mean, so the sorts of things that people have done in terms of understanding how our brain works with probes, things like Neuralink, where you can read out the outputs of thousands of neurons. The technology right now is reading a very tiny fraction of our neurons. So even we're not there in terms of our ability to collect the data that shows how our brain works. Our brains work quite differently operationally than the way neural networks work. Each node and each of our neurons are connected to many, many other neurons. They're operating in the high noise regime. They operate. They use actually much less energy for operation, but a much. But they're much.
Try to make somebody blind, senseless, and without noise or anything like that. Your brain cannot function.
They're much. We operate very differently. I mean, my favorite thing, the many interesting neuroscience facts, like if I keep your eye focused on the same location, you go blind. You actually only are sensitive to changes. So we operate very differently. That said, I don't think we know enough about thought to know, are we fundamentally different from AI or not? I think we don't understand. Perhaps we even understand less. I think we understand less about our own brains than we understand about neural nets. Right? Neural nets are ones we have better control and we're able to get in. There's much we don't understand about it. So thinking about how we're struggling to understand how human thought works. I do not work on AGI, but I listen to different people who work on it. There are people I know well, like Jan LeCun, who is one of the developers of these backpropagation, CNN, right? And Jan believes that the current architectures will never achieve AGI. It's just not the right approach. There are other researchers in the field. Sam Altman believes that this, who's the leader of OpenAI, this will all happen tomorrow. And so I don't, I think we just don't know. Clever people who think much more about this than I do have come to different conclusions. So as a student, I will teach you the most useful phrase I have learned in giving talks when you're asked a question that you don't know. I don't know.
Thank you, David, for your answer. I just have a comment because you mentioned that we need to take sorts of smart people only, but we need heterogeneity. So we need to ask many different people. And as Amos Tversky, almost Nobel laureate, mentions that while my colleagues study artificial intelligence, I study human stupidity. Yeah, so
well, this is something that one of the problems with training on the data we have, right, and this is something Svetlana's pointed out to me in mathematics, people don't publish their wrong results. They don't publish their failed attempts. And one of the things that's one of the bases of our understanding is all the things we tried and failed. And so it's missing in our training data. And we in some ways need a richer training data. This is actually a general AI-independent criticism of scientific publication, is people don't publish failed drug experiments. And when you do meta-analysis on the effectiveness of a drug that uses a lot of different data across the literature, people get wrong conclusions because the negative results don't get published. So I think if we're going to echo Tversky, if we're going to do training, we'll have to train on smart people and dumb people.
There is another ingredient that I think is crucial for a human way of acting, which is curiosity, right? I don't know how to quantify that, but curiosity is probably the main driver towards discovery, right? And I don't know what curiosity means. I know exactly how I can be curious, but I don't know how to quantify that and how to put that in a neural network. What does it mean, curiosity, right?
Yeah.
Mathematically, how can I implement that? I don't know.
Thank you. So now question from a mathematician.
Yes. Thank you very much for your talk. I am a mathematician from Lviv University. One comment concerning the truth. So we are here in Lviv. Banach and others, but on Lichakiv cemeteries there is also Twardowski and his pupil Tarski. He has a theory what is the truth, his main achievement. So we mathematicians do have absolute notion of truth, right? I, as a mathematician, I see that we are a bit happy because we are thinking differently than AI. Because for AI, data is sacral word, right? So data must be very qualified. In mathematics, there is no word data. There are axioms and proofs, okay? And so mathematicians, they closer to chess, basically. So you know rules and you just play. And my nightmare, by the way, in AI. So this AI, I am not afraid of this one. Because he is hallucinating, he is thinking, whatever. I am very afraid of AI, which is plays with itself by strict rules, So you know how to prove theorems, you know axioms, You just create theory, and the other portion of AI criticize, and they just go around and they create their own data, sacral word, but they are absolutely true because they are made from axioms by logical arguments, and they are absolutely true, and it can evolve in spiral far beyond human ability. So the question, how far we are from that point?
Well, the most dramatic example of that is playing with a set of rules is Go, right? Where Go is a well-defined set of rules, if you like, a well-defined set of axioms. There is a right or wrong answer. You win or lose. There's an outcome. And there's a set of steps. And it's not something that large language models do is all very probabilistic. And to me, I think of the way those models work in the language of probability and likelihood function. Given A, what's the probability of word B? Go is not probabilistic. It is closer, if you like, to an axiomatic problem. And it was a problem that was thought of as being, I mean, when I was a student, the mathematicians playing Go at Fine Library at Princeton looked down upon everybody. And I remember my Go players talking about their kind of almost moral superiority to anyone else because of the complexity of Go and the high dimensional space that Go represents, and that this was an example of an unsoluble problem by computers because of the dimensionality of the space. Right now, computers are much better than any human at Go. They have discovered moves and types of moves that are not understood. So that's the closest we've gotten, right? Doesn't mean they've proven any important theorems yet. What I think is on the horizon is very different, in a way, whether you put this under AI or not, very different from machine learning, is formalization of mathematical papers into a set of rules. And I don't think we're anywhere there, we're not there yet, but one could imagine that we have these computers that have formalized a lot of mathematics. They can explore some space using those formalized rules the way you explore Go. I'm really talking about possibilities. This is not something I would say with any confidence and just sort of really speculating, but Go is the closest thing I can think of to the example. I think it's hard to know whether that's our future. I think it's hard to know how far these will go. We have seen in many ways in the last decade or so an exponential improvement by many measures in the performance of things like large language models. And it is unclear when exponentials always saturate. It's unclear when they saturate. If you look at the performance of a network versus data and compute, it scales as compute used to some really low power, like 0.05 or something. It costs you an enormous amount to double performance. Doing that requires energy use. We have a limited amount of electricity. We have a limited amount of data. They've basically used everything on the internet. So it is possible that it'll saturate. Moore's law effectively saturated. The cycle speed on a computer doesn't improve anymore. So it could be that, this is as far as, we'll get another doubling by some metric in the next few years, and that's it, and we'll see it applied to a bunch of problems, and it'll be important in the next 10 to 20 years, but it will be not quite a fad, but just something that develops and goes away. Or it could continue to improve, and we don't know.
Yeah, there are many questions. Sorry, Taras. Actually, I saw a question from the economist and a physicist. So,
good evening. Thank you very much for this presentation. It was gorgeous from intellectual point of view. Really, thank you. And my question is a bit speculative, and I would have to oversimplify some things, so please forgive me. To some extent, the AI, as it is right now, is following our consciousness. It's doing the job we already was capable of doing, but a bit more energy effective, a bit more following the rules we are setting to it. So basically, it's not smart enough. And as the colleague brilliantly highlighted, we still have math, we still have our ability to fake consciousness, and so on and so on. So we have some sort of intellectual superiority over AI, and we reserve some distinctive features of our consciousness. So to some extent, we can say that it differs from ourselves. But a couple of decades ago, Deep Blue gained superiority in chess, and recently AlphaGo gained superiority in Go. Moreover, AlphaGo had showed some debuts which was unknown. So it's not only superiority, it is inventing superiority. So we are kind of pursued with the consciousness of AI. I am speculating. From the other perspective, around the mid of 20th century, the very famous quote was sounded: "Shut up and calculate." So to some extent, we're already bumping the ceiling. We already hit some sort of notions we don't understand. So we have limits of our consciousness. So my question is, are we between the hammer and the envy already? Or there is some other dimension and my speculations are wrong? Please comment.
So I'll take a historical perspective on this. Much of our ancestors were mostly peasants in the field. And what humans mostly did was, take a hoe and hoe the earth, right? That was what took up 95% of human time and energy. We were replaced by mechanization, and agriculture, I don't know, employs 5%, something like that of the world. Some ever declining fraction of humanity grows food. There's some specialized things like making good wine, where there's areas of specialized knowledge, but machinery, not computing, machinery has replaced humans there. Same is true with manufacturing. My ancestors were tailors in this region. Everything they do was basically replaced by high-speed machines that are now mostly operating in places like Vietnam, right? So this humans used to spend a lot of time doing a bunch of things. Now we don't. I probably spent far too much of my life filling out travel forms. And there are a whole bunch of things where I am confident machine learning will replace that. And I think there are many jobs that will be replaced by machine learning. It is very difficult to get a starting job as a lawyer or a computer programmer right now in the United States because AI is replacing those things. And I think because it does, the way AI operates is so different from human thinking, there's a set of things that it will mean we don't do it anymore. I began by talking about adding and subtracting large numbers, which people used to do, and accountants would spend time doing, and there was a real skill in doing that. And at this point, calculators, just simple calculators, do that so much better than we do. We just use them as a tool. We don't do those problems. There'll be a set of things that AI can do that we currently do, and it will do more effectively than humans. and we'll just assign those tasks to AI, and we will do other things that AI are not so good at. What's interesting about, there are parts of science that maybe, there's this quote on quantum mechanics, understanding the meaning of quantum mechanics, which is, stop worrying, just calculate. At this point, calculating solutions to quantum mechanical equations and representing solutions in high-dimensional spaces, I think AI will actually turn out to be a very powerful tool, or machine learning, for doing that. So we will be able to do better calculations. It's already been true that before what we call AI, people have been doing calculations in general relativity where they make use or calculating Feynman diagrams, where you make use of computer tools to do calculations. I think we should do more than calculate. I think there are fundamental questions in quantum mechanics that we should be thinking about. And in fact, the rise of quantum information theory has sort of reinvigorated this, and we're again thinking about those questions. And since I spent most of my career as a cosmologist, I would say to me, the fundamental question in cosmology is, how did the universe begin? And we are unable to answer that question because we don't understand quantum mechanics. So we have, and I don't see in its current state any way in which AI will make progress in understanding the nature of quantum reality. So there's other work for us to do. In a way, it may mean that the easy work of just doing calculation may no longer be accessible to us. Our computers will do it better. We'll have to do other things. But it's a very interesting question.
Thank you, David. And I'm afraid we have the last question.
Thank you. Thank you so much for your talk, and many thanks to all for this very interesting discussion. Actually, my question is inspired by Svetlana's past question. She asked you if you remember that now it's hard to judge, especially in mathematics, what is truth, what is not. And for me, it was a perfect question from a mathematician. And then your answer was, as I understood it, perfect answer from somebody doing empirical science. You told, it gives me more knowledge about the universe. And as Taras Banach mentioned, that somebody is buried here on Lechakiv Cemetery who defined what is truth, but also somebody else who was Karl Popper, and who told that science is something which can be falsified, right? So in this sense, in empirical science, we know how to judge. Now I am coming back forward to my question. So far we were talking about sciences in English, so to say. But if you say Wissenschaft, you have Geistwissenschaft, you have other Wissenschaft, which is natural sciences. We never touched humanities. And if I look on this question and on this answer, which is now on the whiteboard, and if I think about humanities, so for me it seems that the way AI is used there, that's basically it's more misused as used properly. Because, well, what is your opinion about this?
So,
thank you.
It's in a sense a very broad question, because what we call humanities ranges from everything from writing poetry, where AI is capable of writing bad poetry really quickly. It writes poetry better than I do. I've asked it to generate things and translate my prose into poetry, and it's fun to watch. But one where I say something more quantitatively, and where I think there actually is some exciting possibilities, is digital humanities. So this is something that looks more like science, in that you'd have large data sets, like all of Shakespeare's writing, and you can then query it and ask for patterns in use and patterns in how it shifts. And, you know, there's things which it's, you know, it's very good at outlier analysis. So if you were to give it all of Shakespeare's writing for training and ask, is this poem look like other Shakespeare poems? It's good at answering that question. Now, that doesn't actually answer the question, was that written by Shakespeare? Because many artists that I know will have a certain style, but will also grow as artists by experimenting and trying to do something very different. So just because something looks different doesn't mean it's not done by that person. But you can, you know, as a tool to ask the question, is it different? I am most familiar with humanities in the United States. I would say humanities in the United States has been going through a crisis of identity for the past almost 20 years. That there was historically a sense of a focus on what was truly great in literature and what research looked like. And I think that became accused of elitism in a way in which there are a lot of guns pointed inwards in the humanities community. And it has undergone a bit of a collapse in that whether you measure as number of majors or centrality to culture, which is perhaps more important, I think there's a bit of there's a crisis in humanities that stands outside of AI. I'd actually be interested, maybe this is something over drinks. Humanities in the Ukraine is in an interesting place because of its emergence and still relatively, not alone the war, but just the relatively recent independence. In that the culture is so central to one's identity that humanities plays a central role in that definition. I saw a wonderful exhibit in Copenhagen on the role of the humanities in Denmark in creating identity as the country emerged in the 19th century. I suspect, and now I'm getting much further outside of what I know than a few of the AI questions. I suspect that humanities in the Ukraine may be at a very interesting moment because one is really understanding the culture in a deeper way and in ways in which it could not have been studied in the 1970s. So that it makes this an interesting time. It has more, humanities in the United States is not at that moment. And I would say is actually under harsh attack from the right and sort of struggling to figure out where it is. And I think those questions to me, when I engage with my colleagues there, are much deeper ones than the role of AI, which I think will just be in the humanities a tool for asking certain questions. So let me thank you for all the questions. This was a really stimulating discussion, and I think shows what an interesting moment it is to engage with this. So thank you all.
Thank you so much, David.